Welcome to the next video, everybody. Today, we're going to prove a crucial result on complete intersections needed to prove the algebraic criteria used in the proof of Fermat's last theorem outlined in the previous few videos. Okay, so the main result of this video will be the following. We'll call it proposition 3. Let O be a complete Noetherian local ring. Let A be a finite flat O algebra that looks like O double bracket x1 through xn mod f1 through fn. We want to make sure that f1 through fn, the ideal, is contained in the ideal x1 through xn. Let's write each fi as the sum from j equals 1 to n of some gij xj, and we'll let D be the image of det gij in A. And finally, we'll let I sub A be the A ideal x1 through xn mod f1 through fn. Then two things are true. The A fitting ideal of I sub A is nothing but the A annihilator of I sub A, and those are both just the ideal generated by D. And then two, the A ideal D is a direct O summand of A of O rank 1. Okay, so let's get into the proof of this, and we'll use this in the coming videos. All right, so let's let P be O double bracket x1 through xn, and we'll let F be the we'll let F be f1 through fn in P to the n. Okay, so a multiplication by G sub ij is, of course, a linear map from P to the n to P to the n. And it sends x, which is x1 through xn, to f. Okay, and this induces a morphism of causal complexes k dot fp to k dot xp. So see my previous video on the basic theory of causal complexes needed to understand this. Since A is finitely generated as an O module by assumption, the P ideal f1 through fn, of course, contains a monic polynomial P sub I in P bracket xi for each I, so you should check that. That's easy. Then P sub 1 through P sub n is an O bracket x1 through xn regular sequence. That's also an easy check. Since completion is exact, which is a basic abstract algebra fact, it's also a P regular sequence. So we can pass from the polynomial ring to the ring of power series. By a result from the previous video, the homology groups then of both causal complexes here have to vanish. And if you interpret what that means in terms of plain down-to-earth language, it says you get the following commutative diagram with exact rows. The top row is just 0 to P to P to the n. P to P to the n is just F. And then we map P to the n to itself a bunch of times. And then we have P to the n maps to P via F. And then we have P maps to A via the obvious surjective map. Okay, and then the bottom row is almost the same thing, except for F has been replaced by X, right? And then instead of P mapping to A, we have P mapping to O. Okay, and then what are these vertical maps? They're all just, well, the map P to P is the det gij map, but then the maps P to the n to P to the n are the actual gij maps themselves that we talked about in the previous slides. And then the map from P to P is, of course, equality. And the map from A to O is just the natural structure map pi sub A. Okay, and so the point here is that the rows have to be exact since all the homology groups vanished. Okay, the kernel of this map, remember, is nothing but I sub A from the proposition. Okay, so we have this commutative diagram with exact rows. If we tensor this diagram on the right with the P module A, then since the rows of the diagram were P-free resolutions of A and O respectively, the homology groups of the resulting rows post-tensor will just become the Tor groups Tor PJAA and Tor PJOA respectively. Okay, and so this just gives us another commutative diagram as follows. So we have 0 to Tor Pn of AA to A to 0 to A to the n, and 0 to Tor Pn of OA to A to the n. And what are all these maps? These maps here are just the rows that result from tensoring, okay? This map here we'll call pi sub A star. This is an induced map from pi sub A. And then this map here from A to the n is just X. The vertical map from A to A is just D. And then the map here that will make all this commute, I suppose, would just be the 0 map, okay? And so what does this tell you? This tells you that this guy here, so Tor PNOA, is nothing but the A annihilator of I sub A, okay? Because here we're looking at the image of D. Here is the X map. So this has to be the stuff in A that dies to X inside F1 through Fn. But if you look at the A annihilator of I sub A, that's exactly what that is. Okay, so it's the injectivity of this map plus the fact that this map is D plus the fact that this map is X. Okay, So we have this isomorphism here. Okay, go back to the original P resolution of K dot FP and tensor on the left this time with the P module map pi sub a from A to O. Now it's a standard fact from homological algebra that Tor functors can be computed using resolutions of either argument. And so we get the following commutative diagram with exact rows, which looks pretty similar to the one we had above. So we have 0 to Tor Pn A to A to the n, and this last map here is 0. This is just the standard kind of map that you get after you tensor. And then we get 0 to Tor Pn OA to O to the n, and this map here is again 0. This map here is the same pi sub a star from the previous diagram, and this map now is pi sub a. Okay, and this map here is actually pi sub a just in each coordinate. Okay, now what does this tell you? I'll leave it to you. It's a quick little diagram chase. The commutativity of this diagram implies now that pi sub a star is surjective. Okay, but you see, we already have, and I think I showed this in the last video or maybe 2 videos ago, the ideal generated by D is certainly in the A fitting ideal of I sub A, and that's certainly in the A annihilator of I sub A, right? But I claim that the surjectivity of this map actually gives you that the ideal generated by D is nothing but the A annihilator of I sub A, okay? So why is that true? Well, we have containment, right? And then the fact that this diagram tells you that pi sub a star is surjective will give you that everything, here is here. Why is that true? Go back to this diagram. If it was surjective in that diagram below, then it's surjective here too. And so I'll leave it to you to check then that everything in the A annihilator of I sub A then actually has to be in the ideal generated by D. Okay, and so we get equality. Okay, so because of this string of containments here, then we have to have equality everywhere here. And so this proves the first part of the proposition that these are all equal. Also, the commutativity of this diagram just tells you because of the fact that the ideal generated by D is this guy here, that the ideal generated by D is free of rank 1 as an O module. This line will give you that. Okay, so to fully prove part 2 of the proposition, you have to be working over A. So what you do is you apply what we've just proven to the complete intersection A tensor K over O over K to find that D tensor 1 can't be 0 and A tensor K over O. A consequence of that, I'll leave this as a quick exercise to you, is to check that D can't be in the maximal ideal of O times A. By Nakayama's lemma, D can then just be made part of an O basis of A. And so the inclusion ideal generated by D and A will have to split as an O linear map. And that will finish the proof of part 2. Okay, so let's look at some important consequences of this proposition. The first corollary is that in the situation of the above proposition, proposition 3, if O is a field actually, then the ideal generated by D is actually the unique minimal non-zero ideal of A. This will be a fact that we'll use. So this is easy. So by the proposition, the ideal generated by D has dimension 1 over O, which is just K, right? And so the ideal generated by D definitely doesn't contain any smaller non-zero ideals. On the other hand, it's a completely easy check that every minimal ideal, let's say frac A, is annihilated by the maximal ideal I sub A of A. This is really just definitions in algebra. And so again, if you use the proposition, you find that the A annihilator of I sub A is just the ideal generated by D. Okay, well then frac A has to be contained in D. Okay, so these 2 facts then come together to tell you that the ideal generated by D is just the unique minimal non-zero ideal of A. Corollary 2, last slide of the video. So we'll let A be a finite flat O algebra with section pi sub A from A to O. And we'll let I sub A be the kernel of pi sub A as usual. If A is a complete intersection over O, then the A fitting ideal of I sub A is just the A annihilator of I sub A. And this ideal is a non-zero direct O summand of A. This is really just a proposition, but you replace x sub I in the proof throughout by x sub I minus pi sub A of x sub I, just to make sure that the proof tracks through and you have all of your assumptions in place. Okay, so because after all, remember we modded out by x1 through xn in the proof. So that's kind of what this functions as. All right, so we'll start applying this proposition next video. So remember, our goal is to prove these two algebraic criteria for isomorphisms of complete intersections used in the proof of Fermat's last theorem, and we'll get started on that next video. All right, so I'll see you then, and thanks for watching.